In this video, we are going to use the second derivative test to find the local minimum and local maximum of a function. There is a big what if. What happens if you are unable to determine concavity? So what do I mean by this? Let's use these two problems to explain. So for number 2, we have a f of x. So I gave you f prime and f double prime because I want you to double check your work. Make sure you do not mess up the derivative. If you mess up the derivative, you mess up the critical number, then the entire problem is wrong. So we have f of x. So let's quickly do f prime of x. So using simple power rule, we have 4x to the third minus 12x squared, right? And then we set that equals to 0. Second derivative test. Second derivative test is not asking you to set the second derivative equals to 0. Second derivative test, you still set the first derivative equals to 0. I have the procedures right there. I am not going to read this off. If you want to keep a record for yourself, you can take a screenshot and then drop this, write everything down over to your notebook. All right. And then set that equals to 0, and then we factor. I'm going to factor our 4x squared. We have x minus 3 equals to 0. So we have 4x squared equals to 0, and then x minus 3 equals to 0. That is called a zero product property. I need to remind you to apply zero product property, the other side must be a 0. If the right hand side is any number other than 0, then the zero product property is not going to work. So this one gives me two critical numbers. One is x equals to 0, one is x equals to 3. So they are my critical numbers. So let's box them and then call them critical numbers. All right, and then we proceed to the second derivative, f double prime. So using simple power rule again, we have 12x squared minus 24x. This one, let's put this in factor form. I'm going to factor out 12x, and then we have that multiplied by x minus 2. We are not setting this equals to 0, so that's all we have to do right now. And then we are going to plug in the critical number to the second derivative. So let's quickly review the concept of second derivative. So here is what happened. You found critical numbers from the first derivative, and then you plug in the critical number to the second derivative, right? So after you plug in an x to the second derivative, you are going to get either a positive, negative, or 0, right? So the second derivative tells you this. You plug in a critical number to, let's say, the first one, to the second derivative. If the result turns out to be less than 0, so less than 0 second derivative, the concavity, the function is concave down, right? Second derivative negative, we have a concave down function. And then what is a critical number on the first derivative? The first derivative, you have a critical number. That means that number is either a max or a min, so you have a concave down. So obviously, there is a local max, right? And then what if the second derivative, the other critical number is greater than 0? So that means the function is concave up. Critical number tells me that that number is either a min or a max. So since we have a concave up, then this point must be a minimum. So using this method, we don't need a sign chart at all to find the local max and local min. So the second derivative helps us to skip the sign chart. We don't need to test any interval. We don't need to choose test value. We don't need to test the first derivative. So that's how convenient the second derivative method is. But there is a what if. So as I move on to the next step, you will see the what if. So now let's do the plug-in, right? So you plug in a 0. So f double prime of 0. You have 12 times 0, and then 0 minus 2. So 12 times 0, the entire number is equals to 0. Okay, so let's hold on to the 0. I'm going to write something about it, and then let's handle the other one. So 3. So that is 12 times 3, and then 3 minus 2. I don't care what that equals to. If you do the math, you can quickly find out that that is equals to 36. But the most important thing that I care about the most is 36 is greater than 0. So using second derivative greater than 0, so that means the function is concave up when x is equals to 3. So when x is equals to 3. So we have a concave up, and then I found this using x equals to 3. That means at x equals to 3, we have a local minimum, right? Greater than is up, less than, greater than is concave up, less than is concave down. What about equals to 0? So equals to 0, if you go back to the second derivative using the sign chart, the equals to 0, that means we have an inflection, right? When the concavity changes from up to down or from down to up, there is an inflection point. So this one basically is an inflection. So that means we are using the result equals to 0. We are unable to determine the concavity because at x equals to 0, this is only an inflection point. But can we still find out what happened when x equals to 0? The answer is yes, but before we do that, let's locate the local minimum. So I know that there is a local minimum when x is equals to 3. Can you tell me the exact location of this local minimum? Yes, to find the exact location, then you have to consult the original function, f of x. So you plug in f of 3 back to the original function. So the original function is x raised to the 4th power minus 4 times x raised to the 3rd power plus 2. So you have that equals to negative 25. That means an order pair 3, negative 25 is your local minimum. All right, and then what about x equals to 0? So if you want to find out what exactly happened when x equals to 0, then you have to go back to the sign chart using your first derivative, right? So this one, I am going to go back to my sign chart because this one, I don't want to just leave that as unable to determine. I want to find out what happened. I need a more solid proof, all right? I don't want to leave my word right here. I want to give myself a more solid proof. So to get to the solid proof, we have to use the first derivative and the sign chart. Again, we have two critical numbers, right? One at 0, one at 3. So that gives us 3 intervals. All right, so 3 intervals. Then we have negative infinity to 0, and then from 0 to 3, and then from 3 to positive infinity. Again, I am doing everything for the first derivative, so that means I have to pick a test value. So let's pick something easy. Negative 1, x equals to 1, and then x equals to 4. Pick a number that is inside the test interval, and then you plug it into the first derivative, f prime. So you found f prime, right? So you plug in the negative 1, you plug in a 1, and then you plug in a 4. You have to determine whether that is positive or negative. I did the math already, so this is negative, and then this is positive. So negative means we have a decreasing, positive means we have an increasing, and then at x equals to 3, there is a minimum, right? Going down and then up, we have a minimum, just like the conclusion I drew right here. We have a local minimum. And then what about x equals to 0? So x equals to 0, then this is not a max or a minimum because the function is keep going down. So when x equals to 0, the curve is going straight down. So there is no mean, there is no max. If you are talking about concavity, 0, when x is equals to 0, there is a concavity. So that's all I can tell you. So there is one local minimum at 3, negative 25. Only 1 point only. All right. So moving on to number 3. So let's switch color for number 3. Number 3, the function that we have is f of x equals to x to the 2/3 and then minus 3. Okay, so let's find the first derivative. So first derivative, we have what? We have 2/3 x, and then 2/3 minus 1 is negative 1/3. The derivative of 3 is equals to 0. So that is our first derivative. And then you have to set that equals to 0, right? So you have to set that equals to 0. So you have 2, and then divided by 3, the cube root of x equals to 0. Are you able to solve this? What can x be? So if you multiply both sides by the denominator, you have 2 equals to 0. Think about this. 2 divided by what number is equals to 0? 2, think about this. 2, just a simple math. 2 divided by a number equals to 0. Do we have such number? The answer is no. You take 2, you want to divide it by a number equals to 0. That is not going to happen, right? So this one basically, we can solve it. But I can emphasize that x cannot be equals to 0. All right? So x cannot be equals to 0. So that means when x is equals to 0, the function is not differentiable. Okay? And then what is my critical number? Then x equals to 0 is my only critical number. Remember, when you use the first derivative, you have to also determine that what number makes the function fail to be differentiable. That is also count as a critical number. All right. So if you look at the original function, the cube root, right? So there is a 2 over 3. So the 2 over 3, the denominator 3, so that can be written as this, right? So x squared minus 3. If you look at the domain of f of x, x can be any value you want because the cube root of 0 is equals to 0. The cube root of positive is okay. The cube root of negative is also okay. All right. Remember this, the cube root of negative a is equals to negative 2. But if that is a square root, then we cannot take the square root of negative a. Okay, so we found one critical number, and then let's proceed to the second derivative. So f double prime, and then you bring the negative 1/3 down, you have negative 2 over 9, and then negative 1/3 minus 1, you have negative 4 over 3 equals to 0. So let's get rid of the negative exponent. So that is 9. So that is x to the 4 over 3. You can use radical, but you don't have to. Okay, what do we do next? Using second derivative. Again, the purpose of this problem is practicing second derivatives. So practicing second derivative, you have to plug in the critical number to the second derivative. You have to plug in this 0 right here. So you have f double prime of 0. Because you want to determine is that positive or negative, right? So you can determine the concavity and then you can determine the mean and max. But unfortunately, once you plug in a 0, look, 0 raised to 4 over 3. That is not solvable at all, right? So this is undefined. So that means using the second derivative, we are not able to determine whether that is a mean or a max. So that when that happens, you have one critical number, you plug in, there is nothing you can determine using the second derivative. So that means this one, we have to use the first derivative test. And that's why I picked this problem for our discussion. All right. So when you see this, then we have to use the first derivative test. What is the domain of this function? The domain of this function is this function. The domain of this function is x can be any real number, right? But if you consider the critical number, so that means yes, x can be any number, but when x is equals to 0, the function is not differentiable. So that means when you draw your number line, you have to omit the 0. So you have to put a 0 right here. Then therefore, that gives you two test intervals from negative infinity to 0, from 0 to positive infinity, and then you test your interval x equals to -1, x equals to 1. Again, don't pick big numbers to torture yourself. Since we are using first derivative, then we plug in the 0, then we plug in the test value to the first derivative, -1. So that is 2 divided by 3 times the cube root of -1. So that is equals to -2/3. That is less than 0. And then f prime of 1, that is 2 divided by 3 times the cube root of 1. That is 2/3. This is greater than 0. Remember the previous problem is keep going down, right? We can determine mean or max, but this one is not. This one is less than 0 decreasing, greater than 0 increasing, and then at this point it's not differentiable. It's okay, not differentiable. We don't have a horizontal tangent. That is totally fine. So we can still conclude that there is a local minimum at x equals to 0. All right? And then can you tell me the exact location? All right, to get exact location, you have to plug in the x equals to 0 to the original function, which is x raised to 2/3 minus 3. Simple math equals to -3. That means the order pair when x equals to 0, y equals to -3 is my local minimum. So that's how you solve this problem. If you think my video is helpful, please click the subscribe, give me a like, share this video out. I will keep making more and more videos on my channel. I see you all in the next lesson.